As we showed on Monday's plenary presentations, Spatial Technology enables location master data management. It allows you to use automated rules to do several things. Those things include measuring and improving data quality, preparing and migrating data to a different system, synchronizing data to propagate updates between systems, or to infer and generate new data. And this applies both for internally data within an organization, but also when matching data between organizations to cross-reference it or link it to an authoritative source. And from that, we can start to build some semantic meaning between the data sets and infer new information. The OneIntegrate rules engine is complemented by the One Data Gateway portal. This provides controlled access to authorized users to run the rules in an easy-to-use portal for uploading the data to be processed. One Data Gateway can be used for a number of data automation use cases, so that could be data validation, data improvement and enhancement, such as propagating and linking to multiple networks, or it could be data acceptance and ingest of supply chain data. Over the last year, Spatial Technology has been driving forward, and I'll talk about some of the developments here. For OneIntegrate, our rules engine, we've been expanding the range of data access formats. So for example, we can access Google BigQuery data, read and write to it, access directly to Esri feature services. We're adding access to web feature services, and that includes accessing the OS Data Hub. And also true 3D data, being able to read it, validate it, process it, and write it back out. And in parallel, we're expanding data operations in the product. So for example, integrating with machine learning libraries, and we'll see some examples of those later, and generally expanding the capability and power of the rules engine. One Data Gateway has seen some major releases, which includes access to any sort of rules that we want to run as defined in OneIntegrate. Powerful user and organization management to control who accesses what and when. And also identity and single sign-on, so integrating with third-party identity management systems. We've added dashboards and analytics and access to that data so that it can be processed either within Data Gateway or in third-party analytics software. And reports on your upload that can be downloaded as a PDF. And also custom branding so that you can color it and brand it so that the site can look with the look and feel that you need for your solution. And then OneSpatial LMAP, which is the application platform for building mobile solutions. These can be running on Android or iOS, and they allow the creation of simple targeted applications. And these have got lots of power and capability because they have the power of the rules engine within them. So you can view, search, edit data, but importantly run rules as you're editing on your mobile device. So examples of applications that we've built for customers are incident management applications or network update applications. This is a location master data management architecture using this approach. Here there's a central enterprise store of data, but it could be one of many sources, each of which masters a different aspect of the same real-world assets. At the top, Data Gateway is providing cloud access to rules-based apps, such as supply chain data ingest, leakage prediction using machine learning to predict leakage risk, positional accuracy improvement to improve the location of assets based on reference data, or automatic generation of traffic management plans. We'll see some examples of those in a moment. These apps allow cloud-based access to the capabilities which depend upon or sometimes even augment the core enterprise data. At the same time, there's integration with external systems, and these might be data services which we access on demand in order to provide reference data. So for the Data Gateway apps, for example, Ordnance Survey Data Hub. These external systems might also be running rules via the APIs or accessing the core data or the dashboard and statistics for analytics insights. The automation that we've talked about in this past is now extended to include support for true 3D data in OneIntegrate. And that means that the current use cases for 2D data still apply now for 2D and 3D data. So use cases of validating data to measure data quality, cleaning data to improve its quality. integrating data from different sources, or inferring new information. A whole range of data formats are supported for this, and this means that it enables whole new use cases for the data. So for example, that could be underground construction, checking for clashes for containment. It could be environmental purposes, use cases for building energy efficiency based on their size and their shape and their location. We've also seen use cases around taxation, looking for line of sight to certain things, looking for the sizes of the apartments within a block and checking they're paying a consistent tax rate. As well as 3D capability in OneIntegrate, there's also the real-world 4D product from OneSpatial. This allows a view of the assets as they are in the real world. So this combines 3D data, 2D data, and any imagery such as LiDAR scans, or here we've got photo textured surfaces that have been captured out in the field. And this allows us, for example, to view the 2D data as it is in the GIS, compare that to the 3D images, and see a first-person view, but also an orbital view that's going to combine imagery from subsurface and above ground. And this can save huge amounts of time before going out in the field. That it can be inspected to check what are the assets down there, what is the condition, what equipment do I need to bring with me before I go down and perform maintenance tasks. Here's another use case that we want to show, and this is an example of machine learning. Here we have a selection of water pipes, clean water pipes for a part of the country, and we're interested in determining the chance of leakage. So what we're going to do is use Data Gateway here to upload a file of data and push that through a model that we've already trained, and that model will predict the chance that a pipe is going to be leaking in the near term. So we've used Data Gateway, we've uploaded the data, Data Gateway has checked that the file format and the structure is correct, and now it's going to read the data and process it. Here we've taken some, in order to train this model, we've used third-party machine learning software. This is Google's TensorFlow that we're using, this library, and we're calling it here from Data Gateway. The model's been trained by taking information about the assets and comparing that with historical leakage or historical failure records. So we consider the length, the age, the diameter, and also which features does it interact with. So is it under a road? Is it under a major road or a minor road? And all these different considerations can be taken in to train the model. Then once the model's trained with the historical data, here we're pushing through some new information to see what it can do, to get a prediction of the chance of leakage. And it will classify essentially into, or we can color code it into high, medium, and low risk. So we can see most of these pipes are now color coded green. We can see some yellow ones and some high risk ones in red. So we can complete that in Data Gateway. We've got our prediction, and that data can now be downloaded and opened in a GIS tool and used to help the maintenance of the data. Now we can have a look at that same leakage prediction data in an LMAP app. So this is an Android app where we're opening the data for that area, and we're seeing the prediction results color coded as before into low, medium, and high risk. This next example is positional accuracy improvement. Here we can see a section of the pipe network where it corresponds to the road, and we need to improve that. So we've got the Data Gateway app, which is going to apply some rules to improve the position of that data using reference data. So I'm uploading some data to the Data Gateway app. It's going to receive that, check the structure, check the format, and then if that's okay, it's acceptable, it's now going to start running the rules. For this process, we're using reference data to infer the shifts needed to get the pipes in the correct position into the road. Those shifts come from all sorts of places. Sometimes they're known explicitly, sometimes they're inferred from the data or from some known points. Here you can see those shifts that have been inferred that will move the data to the right place. So I'll continue to process that data, and that will give us an updated, improved location of the data, which I can then download and have a look at that in a GIS tool. Now I can display the data before it was repositioned and the data after it was repositioned. So here's the background map before it was repositioned. You can see it's not in the correct place, or at least it's not in the road as it should have been, and then the shift vectors showing where it's going to be repositioned, and then we can show the position of the data after it's been repositioned. You can see it's now in the center of the road as it should have been, and we can step between various base maps to confirm that, various reference data sets to confirm that that's in the correct location. The final example that I want to show is traffic management plan automation. Traffic management plans have to be submitted in the UK every time someone wants to dig up a road. They're submitted to a local authority for approval, and they define where the road signs go, where the traffic cones go, where the traffic lights go. And they all need to be created according to a detailed specification, a rule book. In this process, we're showing how we can automate the generation of those plans, and those plans normally are time consuming. People go out into the field, they design their plans in a CAD tool, they submit them to the local authority. This process will automatically generate the plans based on that rule book using OneIntegrate rules. The process of creating plans automatically will use all sorts of reference information. It needs the road network information. It needs the topography around it to make certain decisions. Here, the user is specifying information about, for example, the traffic counts at that road. Information that can be accessed automatically from reference data will be, but where that information isn't available or the user can override it, then the user can specify that information. And then the user simply digitizes, here is the location of my work area. And from this information, the system can do everything else automatically. Once the information is provided, then the automatic process kicks in. And this is where it's going to make use of the reference data in the background, the reference data available for the road network, and it's going to automatically follow the rule books that have been implemented using OneIntegrate rules. The process will search a certain distance. It will look for things like road junctions. It will look for things like the classification of the road. Is this 1 lane, 2 lane? Are there pedestrian crossings? Are there pavements here? And we can see the process count happening on the left-hand side. And as a result, it's going to lay out all of the cones, all of the road signs, and all of the traffic lights automatically in the matter of seconds. The end result is data that's populated in the database, and that can then be generated into a plan, and we'll see that in a moment. Here the assets have been created and we can see them, and let's zoom into those and we can have a look at them in more detail. But we've got the road signs created, we've got the traffic cones, we've got the traffic lights. So now the user is confident that the rules have been followed, the rulebook has been followed. This is a much faster process than doing it manually. And the data that's stored in the database can then be converted into a PDF, and that PDF is what's submitted to the local authority. But there's more than the plan that's created. Because we have the information about the assets, how many there are and what type, then the report contains all sorts of information. So if we open the report, we've got the plan, and we've got the legend, and we can show the layout, but we also have an equipment list, an inventory list. And that's very effective now for making sure that the correct equipment and correct assets are taken out onto the field. It can be done right first time when that needs to happen, once the plan's been approved. Now we can have a look at those assets in an augmented reality application. So this is something that you could use out in the field. You could generate the plan and have a look to see, yes, what would that look like in real life? And so that's an example of the data's enhanced. We've inferred some information. We've generated not just a 2D plan, but we've generated data, and that data can be used in a really powerful way to visualize the planned roadworks before they happen. So we've seen a number of examples of OneSpatial technology, but what people are actually trying to achieve with this software are things like the ability to have digital twins. Now, the concept of digital twins, people have talked about them a lot for several years now. When I first heard the concept of digital twin, it was described as a digital representation of a real-world asset. And I thought, well, we've had that for years. We've had GIS tools and databases and CAD tools. But the digital twin concept is, it's not just a record of the asset as it was when it was installed, because that's what a GIS or an asset management system is if you don't keep it updated with the latest information. So for example, if we're doing network tracing based on a pipe's diameter and depth and slope, if it's gravity fed for example, then we will be tracing the network as it was when it was clean and installed. But over time that would have degraded, the pipe would have been clogged, it would have been sagged. The height might have changed, the condition would have changed, the surrounding information would have changed. And so digital twin is about keeping that information up to date. And typically that means using sensors or some sort of measurements to record that near real-time property of the asset, which means that the network tracing and the analysis can be much more accurate. It can represent how the asset's actually performing now. And that's a key part of location master data management, is synchronizing that information and so ensuring the network is clean and the information that relates to it is kept up to date and synchronized. I've talked about digital twins and some other technologies, and there are many of these buzzwords casually thrown about these days. Everyone feels they need to be on some bandwagon, but in reality none of these is a silver bullet that solves all problems. They're simply tools or approaches or ways of thinking to add to the toolkit and use in the right way. And by using them in the right way, then we can transform what we do and how we work. The common theme with all of these is automation, and there's certainly more of that happening. So if we look at digital twins, machine learning, sensors, smart meters, they're all about automation and automation of the data. Now, automation doesn't mean replacing people. We'll use tools and technology at work, and whether that's emails, video calls, spreadsheets, cloud storage for sharing, they're all marketed as productivity tools, but we're just as busy at work, we're no less busy. It's just that we've been achieving more in the same time. People often say, what did we do before emails? But the answer was slightly less. We knew less about what was happening and shared less information. Now that overload is not necessarily always a good thing, but imagine how slow projects would be if we did the same number of things at the same speed without all of these tools. So this productivity increase is always happening slowly and steadily. Now one example of automation is self-driving cars. A few years ago, great strides were taken and moved these from impossible to theoretically possible to actually in use. But they are only in use in the most straightforward cases. Initially, they've been rolled out on wide US highways in good weather. And the other use cases become exponentially harder. What about country lanes, ad hoc signs and detours? There's a tractor coming towards us blocking the road. And these more complex use cases will take much longer to achieve. So these essentially are more like driver aids than full automation, and full automation will take a long time to achieve. The point is that automation is powerful, but after the initial quick wins, the problems become harder and therefore require more intelligent systems, more effective data, and more effective tools to achieve those use cases and unlock that true potential. Thank you.